In the mid-19th century, raw aluminum carried a market price higher than pure gold. Emperor Louis Napoleon III hosted banquets where standard nobles ate from gold plates, while the most prestigious guests were issued rare aluminum cutlery. This high cost existed despite a surprising geological reality. Element 13 is actually the most abundant metal in the Earth's crust, making up roughly 8% of the surface. The metal remained rare because it is bound tightly to oxygen inside bauxite ore. Separating them required more energy than 19th century technology could provide. Standard smelting using heat and carbon failed to break the chemical bonds between aluminum and oxygen. In 1886, a young scientist named Charles Martin Hall co-discovered a technique known as the Hall-Héroult process, which approached the problem through chemistry rather than simple heat. The process uses high-energy electrical currents to pull aluminum atoms away from oxygen in a molten chemical bath. Mastering electrical extraction replaced the metal's status as a rare treasure with a new role, a mass-produced industrial staple. With extraction solved, manufacturers could finally exploit the unique physical properties of the metal. At a microscopic level, aluminum possesses a strength-to-weight ratio that challenges traditional heavy industrial metals. It weighs approximately 1/3 as much as steel, yet when mixed into alloys, it maintains the same structural integrity. This atomic pairing of lightness and durability overturned the engineering rule that structural strength must come with a penalty of heavy mass. Once extraction became affordable, the metal's weight properties triggered a sudden adoption across nearly every manufacturing sector. It was soon used for everything from rigid window frames and bicycle tubes to thin, flexible kitchen foil. Most importantly, it provided the solution for commercial flight, where every pound of weight affects the ability to stay airborne. Without the weight savings provided by Element 13, the modern network of global passenger aviation would be physically impossible to lift off the ground. This requirement for low mass is critical for space exploration, where vehicles like the Saturn V must be light enough to achieve escape velocity. Spacecraft and orbital stations utilize aluminum because it offers weight savings while surviving the harsh environment of a vacuum. While aluminum is highly reactive, it lacks the destructive oxidation cycle that causes iron to rust and flake away. As this diagram shows, when raw aluminum is exposed to oxygen, it reacts instantly to form an impenetrable oxide layer across its surface. This self-healing barrier creates a permanent material capable of surviving extreme environments where human maintenance is impossible. Beyond its use in space, this durability allows everyday objects to achieve a state of infinite material endurance. Aluminum can be melted down and reformed indefinitely without any loss of its original structural quality. This chart compares the energy requirements. Raw extraction takes a high amount of electricity, but recycling existing metal requires only 5% of that energy. This efficiency explains why nearly 75% of all aluminum ever produced is still in active use today. Recycling operates as a massive energy saver, bypassing the high costs of mining to recover the metal for a fraction of the original energy cost. This energy efficiency makes Element 13 a requirement for the global transition to green energy. Massive solar farms, offshore wind turbines, and long-range electric vehicles all rely on this lightweight, corrosion-resistant material to operate at peak efficiency. The metal that once sat as an imperial novelty on Louis Napoleon's dining table has become the structural backbone of modern global transport. Its true power is its utility, providing the physical foundation we need to build a permanently sustainable human future.